Welcome to RF transceiver design course. We were discussing about the amplifier design. We also discussed the stability in last class. We will go further, and in last class what we have seen that if we want to design amplifier for the maximum gain, we have considered the designing the amplifier for maximum gain. We have also derived multiple gain formulas which are important for the amplifier design. It is useful for low noise amplifier as well as power amplifier. So, it is a common for both. So, that is why we have tried to make it a common for both the amplifier design. Now, we will see further that if we have a specific gain and how can we go for the amplifier design. In last class we have considered a two case. One is a unilateral device or bilateral device. Unilateral, that means there is no feedback out between output to input, and in bilateral you have a feedback from output to input. So, in this case if S12 is equal to 0, that is considered as a unilateral, but if S12 is not is equal to 0, then it is called a bilateral. So, there is one figure of merit that is called unilateral figure of merit. Let us say you have a find out the S parameter of two port networks. You have a two port network available, and that two port network consists of multiple transistor. As in last class we discussed, it can be one transistor, two transistor, it can be differential amplifier. You can make it as a two port amplifier, two port network. Now, in the two port network you know the S parameter, and there is a S12 which is not equal to 0. So, if your S12 which is not equal to 0, still you can consider it as a unilateral by choosing this unilateral figure of merit. So, for many transistors or many transistor network, S12 is small enough to be ignored, and when you ignore the S12, we have already seen that your methodology will be simpler and you can design it faster, and the device can be assumed to be unilateral. So, let it be a bilateral device, but if there is a S12 is very small, then you can consider it as a unilateral. So, the error in the transducer gain, caused by the approximating S12 is equal to 0 is given by the ratio. It is also called a unilateral figure of merit U, that is 1 by 1 plus U square GT less than GT by GTU 1 by 1 minus U square. So, here U is defined as a unilateral figure of merit, and this will provide you the range at which your gain will differ if you consider the your transistor or transistor network as a unilateral or bilateral. So, that difference in the gain, if it is in the range of plus or minus 0.2 or 0.5 dB, you can consider this unilateral figure of merit. Based on the S parameter you can find out U, and you can consider your transistor as a unilateral, not a bilateral. So, this is very important figure of merit to find out that you can consider unilateral or bilateral device. So, let us move to the how we can design the amplifier for various gains. So, that is called expression for GS and GL. So, GS is a gain at the source side, GL is a gain at the load side. So, if you have a unilateral case or bilateral case, you can write a GS from the equation of GT. We can write a GS, that is a 1 minus gamma S square by 1 minus S11 gamma S whole square, and your GL is equal to 1 minus gamma L square divided by 1 minus S22 gamma L square. So, if you have a match condition, if your gamma S is a match conjugately and gamma L is match conjugately with the S22, this is the input reflection coefficient of the transistor and S22 is the output reflection coefficient of the transistor. So, if it is matched conjugately with the S11, your gamma S, you can write Gs max, that is 1 by 1 minus S11 whole square, and similarly you can write a GL max which is equal to 1 by 1 minus S22 square. So, your Gs, so this is a maximum gain at the source side you will get, and this is a maximum gain at the load side you will get, and you already know the G naught, that is a S21 square. So, Gs, now let us say if you do not want to design your amplifier for the maximum gain, you have a certain requirement of the gain. So, that value Gs, so there is a normalized gain factor Gs and GL can be derived, and what is that? Maximum means gain, that is required gain, that is a Gs, divided by the maximum gain, that is a Gs max. So, if you if you divide the Gs by Gs max, you will get 1 minus gamma S square by 1 minus S11 gamma S whole square, 1 minus S11 square. Similarly, for load side, at the load side you want a gain which is a GL by GL max. So, where GL is your desired gain, and you can find the GL max based on the gamma L, which is a match with the S22 conjugate. So, GL by GL max, if you write it down, you will get a 1 minus gamma L square divided by 1 minus S22 gamma L whole square into 1 minus S22 square. So, what is the maximum value? This is a normalized Gs. So, this normalized Gs can have a value from 0 to up to 1. So, all the values are in the range of 0 to maximum of 1. Similarly, GL, because you cannot get more than Gs max. So, when your Gs, so here Gs is equal to Gs by Gs max. So, when your Gs is equal to Gs max, you will have a Gs equal to 1. Similarly, when your GL by GL max, when GL is equal to GL max, it is equal to 1. So, you will get a maximum value of GL, that is a normalized gain factor Gs, or GL, that is a maximum is a 1. So, if you try to make this equation into the form of the circle, so you will get a gamma S minus Gs S11 conjugate 1 minus Gs S11 square equal to square root of 1 minus Gs 1 minus S11 square 1 minus Gs S11 square. So, here what is important, that you can represent the same equation, because you are interested to find out the value of gamma S, and if you want to find the value of gamma S and gamma L, which will give you the desired gain Gs and GL, that will come from this equation, and this equation is nothing but a circle equation, which is a center is given by the Cs and radius is given by the Rs. So, this is nothing but gamma S minus Cs equal to Rs. So, you can have a constant gain circles for the input section, that is a source side, which is given by Cs equal to Gs S11 conjugate by 1 minus Cs S11 square. So, here if you put Gs is equal to 1, this term will be 0, then you will have a center equal to, means your center will be at S11 conjugate only, it is at 1 dot, and your radius is also 0. So, this is at the source side. You can have a constant gain circles for the output section, that is at the load side. So, the way we have written the equation for gamma S, you can also write equation for the gamma L, and this gamma L will provide you the two equation, that is the center of the circle CL and the radius of circle RL. So, this CL here now is depend upon S22 conjugate. So, the angle of your CL is depend upon the S22 conjugate. So, this is a GL S22 conjugate by 1 minus CL S22 square. This RL is square root of 1 minus CL 1 minus S22 square 1 minus CL S22 square. So, this is how you can also plot the gain circle. So, up to now if you go back and see that how many circles that we have studied. We have studied the input stability circle, we have studied the output stability circle to find the stability at the input side, to find the stability at the output side. Now, there is another circles that are the gain circles. So, there is a for different gains you can have a different circle. So, while finding out the optimum gain and stability parameter, you should draw the circle on the Smith chart. You can also use a simulator in order to draw the same. So, what are the attributes? Here the angle of the circles are defined by S11 conjugate and S22 conjugate. When GS or GL which is equal to 1, that is the maximum gain, I already told. The radius RL or RS is equal to 0 and the center reduces to S11 conjugate and S22 conjugate. The 0 dB circle will always pass through the center of the Smith chart. So, if you want a 0 dB gain, that will pass through the center of the Smith chart. So, in order to understand, we will use the same parameters that we have discussed in the amplifier design and we will take one example. What this example says, we have a S parameter is given and you in the last class what we have done, we have find out the maximum gain. For maximum gain we have find out the input matching and output matching. Similarly, here we want a gain of 11 dB and frequency is the 4 gigahertz. So, if you want to go for the gain of 11 dB and frequency of 4 gigahertz, you need to plot the constant gain circles for which is GS is equal to 2 and 3 dB and GL is equal to 0 and 1 dB. And you can get the maximum gain of 11 dB. Either you can use a 2 and 0 combination of 2 and 0, a G naught square is already given, or you can use a 3 and 1, 3 and 0. So, any combination is possible based on the gain that you want. So, let us this is the S parameter given and here we have considered the S12 is equal to 0 in order to make it simple, and here because this is a unilateral case, this S parameter for 3, 4 and 5 gigahertz is given. Here make sure that this S parameter is coming after biasing the circuit and it is given by the boundary for the particular bias. First you need to find the stability. In the last class also we have find the stability, here k greater than 1, delta less than 1, and we need to find the maximum gain. So, what is the maximum gain? GS. So, that is a GS max which is 1 by 1 minus S11 square equal to 2.29 which is equal to 3.6 dB. What is the GL max? 1 by 1 minus S22 square 1.56, it is 1.9 dB. And what is the G naught? It is S21 square equal to 6.25 equal to 8 dB. So, your G2U max is given by 3.6 plus 1.9 plus 8 which is equal to 13.5 dB. So, this is the maximum gain that we get, but what we want is a 11 dB gain. So, either we need to reduce the GS or we need to reduce a GL. So, that is why what we have choose is to plot the circle at 2 and 3 dB. So, here you already have a 8 dB gain of the G naught. So, if you want 11 dB you can get the 2 dB from the GS max, then you should make GL max 2 dB from the GS, and GL you should make a 0, or otherwise you can also get the this is a 3 dB, means here 3 dB, and then this is a 0. Similarly, you can make a 2 dB and 1. So, as per the plot and how the gamma S and gamma L, you can choose any value. So, now we will try to plot the circle. So, in order to plot the circle, what you need is, you need to get the CS and RS, CL and RL. So, here your gain GS is equal to 3 dB, you already know GS max. So, this is a small GS. Now, what are the parameters that you required for calculating the CS and RS? You need a GS, which you already have derived. You need a S parameter, that also already been given. So, based on this you can find a GS and means CS and RS. So, that is this is a CS, you can calculate 0.706, and RS, which is a 0.166. So, when you try to draw on the Smith chart, this is a center and then you have a CS. So, you need to make one line which is the angle of 120, and your CS is 0.706. So, that will come something around this point. So, at this point you will get a maximum GS max, and when you try to plot, this will come here at GS is equal to 3 dB, and there is a circle. So, this point, this angle will remain same, this point will always lie on this circle. So, center will lie on always on this line, and you can plot the GS is equal to 3 dB circle. Similarly, you can also plot a GS is equal to 2 dB circle, where you already know GS max, your small GS normalized gain is 0.691, you will have a CS which is a 0.627 angle of 120, and RS is given by 0.294. At the load side, so when you want to plot at the load side, that is a GL max, you can find a normalized GL by GL, that is a desired GL by GL max. So, that is a normalized GL, and based on the equation that we have seen, for the center of the circle and radius of the circle, you can find the center and radius. So, the here angle is a 0.70. So, there is another line which is drawn for gamma L in order to find the gamma L, and at this point where it is S22 conjugate, you will get a maximum GL max, and when you want GL is equal to 1 dB, that will have a circle which is a center somewhere here, and you will have a radius of RL. And you can also plot GL is equal to 0 dB. So, you can see that it is passing from the when you want a 0 dB, it is passing from this circle is passing from the center of the Smith chart, and you can choose any value, means you can choose a value of a gamma S or gamma L which is touching to this circle. So, here the gamma S value is chosen near to 50 ohm. So, what 50 ohm represent? The center of Smith chart will represent the 50 ohm, and always try to use the point which is near to 50 ohm. So, what is the advantage of that? When it is near to 50 ohm, the passive component that you are adding to match are in lower values. Another advantage is you will get the stable, means your stability, generally stability curves will lie on the periphery, means on the top of the Smith chart. So, in terms of stability also, it is better to choose the point which is near to the 50 ohm. So, there is a less chance of your amplifier will go to the unstable region. So, that is why this is a gamma S that is chosen, and this is a gamma L is chosen. So, that should lie on the circle of the Smith chart. So, what is the gamma s? So, here gamma s and gamma L. So, the gamma s, this gamma s will provide a gain of 2 dB, and this gamma L will provide a gain of 1 dB. So, this is a 1 dB and this is a 2 dB. So, total is 3. So, and if you add a G naught, then there is a 8 dB. So, total gain you will get is a 11 dB, that is your desired gain. Now, the next part is to do the matching. So, how can you do the matching? We have already seen in while discussing the ZY Smith chart and impedance matching, that you can use the ZY Smith chart to do the matching, and that can be done by inductor and capacitor. So, you can use a LC matching, even you can use a Q method or T or pi, any network you can design. So, for example, here for 4 gigahertz frequency, there is a, this is a ZL, means here both the place it is considered ZL, but here this is done for gamma S and this is done for gamma L. So, your gamma S is lying at this point. So, this is the gamma S value and then there is a gamma L. So, this is at the input side and this is at the output. So, what you need is here your input means this gamma ZL which you want to match, that is a 50 ohm, means that is a gamma S, that will correspond to the value of gamma S, and this is a, at the source side it is a 50 ohm, and here it is related to gamma L and it is a 50 ohm impedance. So, this is means at the source side if you want to match. So, this is a point is gamma S. Now, how can you match? You need to reach to this 50 ohm circle, 50 ohm point, and how can you reach to this 50 ohm point? If you come down on the Smith chart. Now, when you are coming down on the Smith chart, you are using a Z, that is a red lines Z Smith chart, and when you are coming down, that means you are adding a capacitor in series. So, this is a capacitor that you are going to add, that will be around 895.6 femtofarad for frequency of 4 gigahertz. And when you go up, so when we are going up on the Smith chart, but we are using a blue line, that is a admittance. So, when you are adding a admittance using a blue line, when you are traveling on the admittance Smith chart, you are going to add the component in a parallel, and that is a inductor, because we are moving up on the Smith chart. So, always remember, when we are moving up on the Smith chart, you are either going to add an inductor in series or parallel, and here we are adding in parallel because it is a Y Smith chart, you are using a admittance Smith chart. So, then you need to add around 2.5 nanohenry of inductor in parallel. So, you can easily match by using a simple LC matching network, and this both value 2.5 nanohenry and 895.6 femtofarad are easily realizable at the on chip by using on chip inductor and on chip capacitor. So, it will not take much area as well, and you can design your matching network on chip. Similarly, at the output side, here this is a point gamma L that we have already seen from the previous Smith chart. This is a gamma L and gamma S. So, if you want to find out the impedance matching, you go on the Smith chart, and when you are going down on the Smith chart and you are using a admittance Smith chart, you need to add a capacitor in parallel, that will be around 595 femtofarad. And then Inductor means when you are going up in order to meet to the 50 ohm line, when you are moving up you are adding inductor in series, and that will be around 1 nano Henry of value. So, this is the way you can get the LC matching at the input side and output side, and when you put all the S parameter and the matching on the simulator, you will get the better input matching, output matching, and the gain of 11 dB at the desired frequency. You can also, so this is the value of gamma S and gamma L, that is 0.33 angle of 120, gamma S and gamma L is 0.22 angle of 70. You can also use a stop matching, means you can use a transmission line. We already have seen how you can use a convert inductor capacitor in terms of transmission line. You can also use a stop matching to do the impedance matching. So, in the if you take a previous case, there is a capacitor and inductor. So, here there is a capacitor and inductor, and this is the input, and at the output if you see you have a, again capacitor is in parallel and inductor in series. This is a output. So, this is the way you can design the amplifier of the desired gain. In the last class we have seen the amplifier for the gain, what is the means gain that we required for the, in the last class what we have done is we have gone for the maximum gain. Now, in this class we are going for the means in this class we have discussed that if we desired a certain value of gain, that is GS or means that is 11 dB less than the maximum value, then you can draw the gain circles, and by using the gain circle you can find out the value of gamma S and gamma L. So, this is how the amplifier design for desired gain and gain circles should draw. Now, we will move to the low noise amplifier design, because we have already discussed the amplifier design at micro frequency. So, now it is important to go for important to design a low noise amplifier, and we already have seen the low noise amplifier is the first component of the receiver, and that will try to because it will improve the sensitivity of your receiver, and it will add very less noise, because your incoming signal is already the noisy signal, and when you are adding a less noise by using a low noise amplifier, then what is happen, due to the Freeze formula your total F noise factor F is depend upon the F1 plus F2 minus 1 by G1. So, it is important that you should have a minimum noise figure or noise factor for the LNA, and it should have a sufficient gain, so that you will have a higher gain. It will lower down the noise effect of the incoming stages. So, here if we want to design a low noise amplifier, how we can consider there is a one noise factor equation which is widely used to design a low noise amplifier in microwave circuit also, or in RF IC as well. So, what we will consider here, that there is a two port network, and we already have discussed that if there is a two port network, and for this two port network, if you want to define the noise factor, it is equal to SNR in by SNR out. Now SNR in, you can write Si by Ni, you can also write SNR out here No by So, because it is in denominator. Now because there is a gain involved, we are considering the amplifier design, we can also write this as a Si by Ni into G into No by G into Si. So, this Si here will be cancelled out. So, what you will get is a output noise divided by gain divided by 1 by Ni. So, here you are dividing output noise, means total noise which is at the output, dividing it by gain. So, that when you are dividing it by gain, that is called the input referred, means you are not considering gain, whatever output noise is there, you are taking it out. So, output noise you are deriving it as a at the input side. So, when you are bringing the output noise at the input side, you can represent it as a noise current I, or you can also represent it as a noise voltage Vn. So, that equivalent noise current at the input side is called the input referred noise current In. It is also Vn at the noise which is voltage noise at the input side. Due to the two port network, it is a input referred noise voltage. So, this is then this will become a noiseless two port network. So, this will be a noiseless two port network, and you already have represented the noise generated by the two port network as a voltage source and a current source. So, here the total output noise power is proportional to the mean square of the short circuit current at the input port. So, this is of the noise free amplifier. So, the noise power due to the source alone. So, here this is a source. So, source is represented in terms of the admittance Ys and current Is, and then you can write F, which is Isc square, because then no longer you need to worry about this total short circuit current Isc square divided by the Is square, that is your source current Is, noise current Is. So, we will discuss more about this equation, how we are coming to the final equation of noise factor in the next class.